So I'm happy to see you all here, and I'm happy to start this wonderful conference. Today we have two tutorials. In fact, it's one tutorial on deep learning networks. And so this is the first part, in which I just very briefly describe what is deep neural networks, typical structures, and some applications. The second tutorial will be held by Sergey Nikolenko, and will be much more detailed about deep neural networks in natural language processing. So these two tutorials, you may see them like first related to AI and second to AINL, just like the name of the conference. So this tutorial will be very, very introductive, and if you feel free about machine learning, you won't be really get interested in the first part. If you are really familiar with deep neural networks, you just may skip all this tutorial. So it's very basic and introductive. So let's start. My name is Andrey Filchenkov. As it was said, I'm an associate professor at Computer Technology Department in my university, and also head of machine learning research group at Computer Technologies Lab. Sorry, just have some. Yep. So just 4 parts. The third one will be the most important and most interesting. Okay, so first of all, let's just talk about what are deep networks and what is the field to which they are belonging. So it's artificial intelligence. There are 2 different types of artificial intelligence systems. Strong artificial intelligence, now it's more popular to say that it's artificial general intelligence, which is the part of artificial intelligence when we want to have a system which functions just like a human brain, or even better. However, no such system exists these days, but maybe in 10 or 20 years we'll be happy to see it. Another part is weak artificial intelligence, and it's a bit simpler because it solves only well-formulated problems within a certain domain, and that is what about, and this is the field to which machine learning belongs, and neural networks also belongs. So usually when we talk about neural networks, we are talking about machine learning, and when we're talking about machine learning, we are talking about weak artificial intelligence. However, there were lots of people, and there are lots of people who believe that neural networks will be a key to strong artificial intelligence. So, in fact, neural networks are not only machine learning. There are lots of fields related to neural networks, such as neural computations or neural computers, which are not, in fact, machine learning. But I'll be talking only about machine learning and neural networks as machine learning algorithms. So usually machine learning is really associated to supervised learning. However, it's not only supervised learning, but we'll be mostly talking about supervised learning. So intuition about neural networks was given by neural networks. The first 2 artificial, and the second are natural. This is a picture of neuron. We all have neurons in our brains, and they build associations with the axons, and use axons to translate impulses from one neuron to other neuron. They get activated when they have enough signals received by other neurons, and then they send signals to their friend neurons. So this is not very precise and very simple illustration of how our brain works. And this intuition was first put into how neural networks as a machine learning algorithm should work. However, right now they are not so really related to our brain. So, neural networks have a very long history. So it starts in 1943, when McCulloch and Pitts suggested a model of neuron. So it was just a linear classifier. However, it was inspired by neuron, and they were thinking about to create an artificial intelligence or a supercomputer system which was built from neurons. However, it was not so easily, and only in 6 years Hebb suggested a rule to learn such a neuron. So after that came Rosenblatt. He suggested neuron. So he suggested perceptron. He suggested a computer which is based on neural computations and so on. And since that time, the interest to neural networks grew very, very quickly. That was until in 1969, Minsky and Papert published a book, Perceptron, which had a very strong criticism about performance of neural networks and even one neuron, and that caused a so-called winter of neural networks. By the way, a year before, Ivakhenko suggested a group method of data handling. In Russian, it's метод группового учета аргументов, to learn neural networks, which allowed him to build a system which now we'll refer to as deep learning system. However, it was quite long ago, and for a long time people forget about these systems. Okay, a breakthrough was in 1974 year when Weber's suggested backpropagation algorithm, which allowed to train a big, network with more than one hidden layer, or even with a hidden layer, because before it was really complicated. Also, it was suggested at the same year by Galoshkin. However, it was published in Russian, so no one cares. Okay, after that time, lots of models were suggested, very different structures that were designed not only for predicting but for other problems, such as coherent self-organizing maps, which solves clustering problem. But the key problem was that if you want to go deep, we found that algorithms such as backpropagation did not work because there was so-called vanishing gradient problem. And that was recognized in 1991 that this is a real problem to make model more complicated and to build more complicated neural networks. So it was so-called second winter of neural networks when just a small community, but very strong community, remain working with neural networks, and most of other researchers try to use more interesting models such as SVM, which get very popular at that time. But still, lots of works were published these years. Situation started changing in 2000, and a real breakthrough was in 2012. Despite all the models we suggested before, it was a really hyping year for deep neural networks, because in that year, 4 very famous competitions were won by deep architectures. The most known is ImageNet competition, when we need to classify lots of images, and 2 PhD students of George Hinton, with their architecture, won this competition with a very, very fascinating result. Also, that year there were 3 other competitions about object detection, about image segmentation, and the one I cannot recall, but still. And also, all these competitions were won by models based on deep neural networks. So after that, all machine learning community, and not only machine learning community, paid a lot of attention to deep learning networks, and it's still growing and growing and growing. So today I'll just give you a very brief introduction to what is deep neural networks and why they are so fascinating. So, first of all, we'll talk about machine learning. Machine learning, just in brief, it's how we can get knowledge. There are two paths to get a knowledge, and the first is to ask experts. So many systems were based on expert knowledge. However, it's not very cheap, it's not universal, and so on. So we'd better have data and try to process data with algorithms which can find knowledge in this data. And these algorithms belong to machine learning field. There are lots of definitions about machine learning. I won't give you any. Just a very brief intuition that machine learning algorithms are algorithms that learn with experience. I do not specify what is experience. Sometimes it's not true. For some problems like clustering, it's not true. However, this is the most general definition can be given. In machine learning, the most popular task is prediction or forecasting. So we want to assign a label or we want to assign a number for an object. Just like we want to predict what a disease a person has or what is on this image or how much money I will receive in 5 years. So all these problems are problems that can be solved with machine learning. And what we want to have to learn these algorithms, we want to have data, and we want to have labels for data we have. So just like if we want to predict if it's a cat or dog on the image, we need lots of images with cats and dogs. Quite simple. Usually when we learn this algorithm, we state this problem as an optimization problem, and we want to minimize error, or we want to maximize similarity of outcome to known labels. All objects are described with vectors. So we have features which describe objects. Just like if you have a patient, there are lots of features like his age, his symptoms, where he have been traveling within last week, and so on, which can describe an object very precisely. So we'll be working with a vector representation. On the slide we can see irises. It's the most famous data set in machine learning. So we have 3 types of iris flower and 4 features which describe them. So for each feature we can just point out pictures. So this is one class of irises, this is the second, and this is the third. What we want to do, we want to distinguish all these 3 classes. So we want to learn an algorithm which can be given a data set of irises and then learn how to find a class of a new, never seen iris, given its feature description. So very useful and very simple thing is just to try to use linear discriminant surface. So we have 3 classes of irises, and we can just draw 2 separating surfaces which are linear and which can separate these 2 classes. So then we say that every iris which is described with features that have values in this subspace belongs to red class. All the irises that have features that belongs to this subspace belong to blue class, and higher irises belong to green class. So it's that simple. This is an architecture or linear model that can perform such a classification. So we have object description. These are features. They are summed with weights. So we multiply each feature on a certain coefficient. Then we use a certain activation function, which in our case can be simple sign. So if the result is positive, we return +1. If result is negative, we return result -1. And this is a simple linear model. However, linearity is not always what we want to have, because in many cases, our objects are not linearly separable. So something like here. And what we want to do, we just want to have some classifier which can predict this discriminant surface, which is not linear, in fact. So there are many ways to build it. And in neural networks, we use composition of neurons. What we do, we just build not only a single neuron, which is linear classifier, but a system or a network of these neurons, which in fact is a composition of neurons. Using these outputs as new inputs for neurons on the second layer, we'll have a new representation of data. So after this transformation, we may say that we transformed our data into a new form. And after that, we use a linear surface to separate them. After this representation, we have data which can be really separated linearly. So with our new inputs in a hidden layer, we have data represented in this space where they are linearly separable. So the key idea here is to just put more neurons, connect them, and use inputs for layers for neurons in this layer as outputs of neurons on this layer. Doing this, we try to reflect how brain works, because there are lots of neurons in our brain. So when a new object comes, we just evaluate its features, send it with a neural network, and it returns us a result. So here we have, for instance, classes of iris objects, and this is our degree of our confidence that it belongs to the first iris class, second iris class, and third iris class. We have 3 levels of confidence for each class, and we choose the most confident class as an outcome of our algorithm performance. So how to learn it? In fact, it's also not very complicated, because it's used stochastic gradient descent. Stochastic gradient descent is a standard optimization technique. The key idea why it was not used before 74, because it's really hard to compute derivative for all weights we want to learn. So when we want to learn neural network, we want to learn all these weights. All these weights and all these weights. So in fact, we are optimizing function which depends on all these weights, or a very high-dimensional weight vector. And it's really hard to compute derivative for a new object. So key idea in stochastic gradient descent was to compute all these derivatives separately. First for these layers, second for these layers. And first we compute, okay, I won't go deep in math, but in human terms, we just evaluate errors on these layers and propagate these errors back to these layers. So we used layers on the next levels to adjust weights on the previous layers. This is why the algorithm is called backpropagation. We propagate error back. However, this algorithm is very good to learn networks with 1 layers or 2 layers, but it's stuck with networks which has more than 2 layers. Because it's so-called vanishing gradient problem. When we try to propagate error back, and if we have more than 2 layers, the resulting errors which we'll be propagating will be really very small. So we'll just stuck and do not change anything in the beginning of our network for a long time. So this is really frustrating, and it prevents building more complicated systems. So nowadays, this problem is overcome, and I'll just give you a brief description of how people use deep learning networks and how they learn them to have a big structures. So so it's really hard to define what is deep architecture and what is deep learning network, what is deep neural network. In fact, if you have more than 2 layers, you may say that you have a deep learning network. Why we need to build such a big system? In fact, there are many algorithms, not only neural networks, which can perform prediction, just like SVM, KNN, logistic regression, and so on, but they are quite shallow. They do not allow to build a very complicated models. Instead, they try to use some heuristics to find separating surfaces, which are quite simple. In fact, it's not really true, but in general, it's so. When we build lots of layers in neural network, we can find such a complicated rules in data which cannot be represented by any other model. Another key thing is that we build in a representation of data which allows us to understand the data itself. So if we have lots of layers, we can not really care about selecting features or just creating new features. We can try to use all these layers to represent our data in a way we want to. So in fact, we perform feature extraction automatically. So there are, if you just wasn't, so okay, that's just more arguments. Okay, I'll just give them. Just some things that helped deep networks to become efficient. First of all, activation function. Usually it was a sigmoid function, then it was hypertangents. However, it prevents to propagate errors back. So nowadays we use 2, in fact a bit more, but 2 most important and 2 most popular activation functions, which are relu and prelu. They are really simple and they are really simply evaluated. And they also help us to not avoid but solve vanishing gradient problem. Okay. Another technique which is also very popular for deep networks is data augmentation. The more complex structure we build, the more data we need, in fact, to learn this structure, because otherwise we'll have overfitting. So, in order to have more data augmentation technique is used, which is to transform and somehow change the data we have in order to have more objects. Just like if we have an image, we can just try to turn it, try to scale it, and so on, add noise to have more data, which will be also labeled. Thus, we can have more problems. So, thus will have more problems represented in data, and our deep network will be used to find these problems. Okay. Another technique which was also invented in 2012 is dropout. The key idea is that we do not want to learn all the neurons. We just want to randomly change output of neuron. So we just, okay, in general terms, we just put a randomization to our network. Why so? Because doing this will prevent our network to get overfitted. So our network had to learn knowledge even with inventions into its structure. So we just say some neurons won't have signal in the terms. In doing so, we just learn a more robust neural network. Also, it's related to Bayesian regularization, but I won't get deep into this. Okay, another technique which is also very helpful is to learn all these layers one by one unsupervisedly. So how does it work? We want to build representation for our data. So first we use only 2 layers, and we try to learn second layer without labels, just seeing data, building it very similar to the first layer. After that, we build 2 layers, and then we build the third and fourth layer. So how does it look like? First, it was suggested with restricted Boltzmann machine. Restricted Boltzmann machine is an algorithm, it's unsupervised algorithm. So we suggest that our data have the following structure. We have hidden variables and visual variables. So visual variables is the feature which we can measure, and hidden variables are some variables which are related to these features, but we don't see it. So we just want to learn this structure, and we suggest that the data is generated by Gibbs sampling, and then we try to find the structure which is the most probable with the given data. So we really don't have to see labels for data. We only need to have data and this suggestion. So learning deep Boltzmann machine, we just try to, how do we do it? We just have the first layer of known features, and we say that second layer has hidden features. So we try to learn second layer. When we learn second layer, we say that these are our new features and use them to learn third layer, and so on. So we do it unsupervisedly. First we learn the first layer, then the second one, then the third one, and so on. This technique was used and generalized to both deep belief networks and deep Boltzmann machines. They have lots of layers. The difference is that in deep belief networks we have directed layers in the end, and in deep Boltzmann machine we don't have directed layers. So I guess that it was really complicated, because I didn't pay much time to details, and the core idea, if you don't know what is Gibbs sampling or you never met something like belief networks, is not really hard to follow. But key idea about all of this, we just want to not to use backpropagation and not to use errors, but try to learn inner representations of data and use these inner representations in all the layers we have. So, okay, let's go to more simpler models. They are convolutional neural network. It's maybe the most popular architecture these days. So how it works? They were designed first to recognize images, and the core idea was that we can use already known filters or kernels which can change our image into a much more reduced form. So an image is a set of pixels, and each pixel, so there are lots of features describing image. We want to reduce this number of features by convolving them into simpler features. So what is convolution? We just use certain kernels or filters, apply them pixel-wise, and so we have pixels, we multiply them on our kernel, and we simplify the dimensionality. For instance, if we multiply all this pixels by this kernel, we'll have blur. If we multiply with this kernel, we'll have the edges of an image. Or if we multiply with this kernel, we'll have a sharpened structure of image. So the key idea was that we just use these kernels and simplify our image, And then we also use these kernels and simplify our simplified image and so on. Doing so will extract much more complicated features. This is visualization of what we had on the first layer. Our neurons have learned how to detect very similar patterns, just like ages or colors. This is second layer and this is third layer. On second layer, structures which neurons can detect are much more complicated. And here we have very complicated structures. Just like we can see head of a bird or a net or something else. So this convolutional network built a very complicated structure which has deeper and deeper representation of data which we have. Using simple filters, which convolve data and subsampling operations, it allows to build very complicated representation of images. So the first network, which can be called a convolutional network, was suggested by Jan Kuhn in 1998. It was quite simple. So first it convolves images, then subsamples. So there are convolving, subsampling layers. After that, it had three layers fully connected as a simple neural network. And it was used to predict digits. So it was trained on MNIST dataset, which was also created by Jan Kuhn, and it showed a very, very interesting performance. So this is one of current neural network. So it's GoogleNet. You can see now it's much more complicated. However, the basic elements of this architecture are the same as in the first convolutional network. So nowadays, convolutional networks have lots of applications. First of all, it's of course image recognition and video processing. However, it's also natural language processing and speech recognition. So just several examples. The system is learned to answer questions about images. It's given an image and it has to find some information on this image, just like number of table, who is presented on the picture, how many objects on the picture, and so on. Okay, another much more complicated system is describe the image. So it works in the same way, but it's more complicated. So it even can answer such a complicated question like, what is the mustache made of? In fact, we don't see any mustache on the picture. So if just, it's bananas in the form of mustache, and the system can find that bananas are in the place of mustache. So the mustache are made of bananas. Okay, so how it works? In fact, we have convolutional network for image processing, and we have word embeddings for word representation. I won't tell you what is word embedding. Sergey will tell you in the second part. So they used, these two representations are used to train a fully connected neural network which can answer these questions. Okay, another important architecture is autoencoders. They are not used for prediction, but they're used for data compression. So what are they? We have input layer, we have an output layer, and we have an inner layer, which is much smaller than input layer, and which is much smaller than output layer. And we want to learn these weights so that the input and output would be much similar as it possible. However, output will be represented with a much smaller number of features, that number. So this is a very basic idea, and it's really simple. So the only thing we have to do is just to collect the data and say that this representation should be the same as this representation. After that, we learn of the encoder and have a data compressor system. We can do so many times. So we can build not only one autoencoder layer, but many autoencoders layers, just like here. So we'll build first, second, and so on. It's kind of similar to convolutional layers or subsampling layers, but they are more general. Okay, so for instance, they're used in bioinformatics. So there are lots of applications, but in bioinformatics, we want to represent gene data that is very big. So there are lots of features about gene compression, and we use autoencoders to represent only important features, which are a combination of input features. This works just as PCA, but PCA that can be learned. In PCA, we find a certain linear transformation, but here we find transformation that fits the data most. Okay, so it's also used, for instance, for document preprocessing. Just like we have lots of documents, we use this architecture. So you see, we just do not squeeze data just once, but we start with 2000, go to 500, 250, 10, and then maximizing it. So we have a very compact and smooth representation for documents. And it's so using this and for representing the documents, we have results which outperform well-known algorithm for dimensionality reduction. So let's compare LSA and autoencoders. Colors represent document classes. So we just built two-dimensional representation, which is really understandable by a human. Okay, another architecture which is second most important and the first in natural language processing, it's recurrent neural networks. The key idea here is that we just want to keep the state of structure. So we have input, output, and we have hidden layers, which are also connected. Just our structure, so this is one neural network for the first object, this is for the second object, and so on. So it has layers that do not only connect the second layers, but also connect themselves. So this architecture is very good for processing sequential data, text, music, and so on. So simple architecture is just like this one. We have connections from input layers, and we have connections with previous layers. So they are summarized, and activation function is hypertangents. However, this architecture is not so popular only just as a recurrent neural network, but it's very popular with so-called long-short term memory, LSTM. So it's a special case of recurrent neural network, which now is the most popular within all recurrent neural networks. And it works in the following way. We just want to keep information about our past, but not only about the past we just seen, but also a deep past. In order to do so, we just need to remember not only the things we have seen a second before, or a word before, but things we have seen long before. To do so, we have inner state which collects and represents our knowledge about previous states. It's also a vector. LSTM has a very complicated structure. So there are 4 gates, and we just talk about all these gates. So first of all, it has cell state. Cell state contains a vector which represents our knowledge about past. this cell state is affected by different gates, which represent the information we want to put into our memories. So first of all, we have a forget gate, which tells us what we want to forget about our memory, in our memory. It has input from the previous, from our previous output, a new object, and it decides what we want to forget. After that, we have input gate. It tells us what we want to add to our memories, which objects we want to add, and how important are these objects to our memory. So, after that, we translate our cell state to new by forgetting something and adding new information. So we just multiply this vector to another vector which may contain lots of zeros or several zeros. That means that we forget something. And then we add new information to cell state. So after that, we have the last output get layer, which tells us what we need to return as an output for the current state. So that's just the architecture. It's not the only one OSTM that can be used. There are lots of types of OSTMs. And this is, for instance, representation for visual question. So this is application in visual question answering. So I also won't get deep because I believe Sergey will talk about this. But still, we just built representation for words and use them to remember what is the question, in fact, and what we had talked before. Okay, so just to summarize, deep learning networks allow us to build very strong models which can capture and represent a very specific and very complicated dependencies in data. Also, some types of architectures are very good in certain problems. And now, deep learning networks are state-of-the-art for lots of domains in machine learning: image recognition, speech recognition, natural language processing, and so on. So all multimedia is, in fact, should be processed with deep learning. They are state-of-the-art for all the problems you can imagine. However, there are lots of disadvantages. First of all, of course, it's really very hard to build a new architecture, understand how the architecture works, or try to tune the architecture, because, in fact, the complex model should be tuned, and it's really hard to tune the model. So, also, lots of problems are related to overfitting, because many practitioners don't use dropout and don't use regularization, and it turns out that they build very complicated model for, in fact, similar dependencies, and they get overfitted. And also, we need lots of data to learn a deep learning network, and we also need lots of computational sources. So nowadays, computational sources is not so big problem. Data is not also a big problem if we're talking about images or videos, but if we're talking about standard machine learning problem, like we want to predict if a Titanic passenger survived or did not, we don't have enough data to do so. Okay, so could you please tell me how much time do I have?
A lot.
Really?
You used half of your time, actually.
Sorry?
You have 45 minutes left.
Oh, really?
Really?
So yeah, just yeah, it was a bit hard. Yeah, I didn't expect that I will come to this point so early. So maybe questions then. I just keep main details, and maybe if you didn't understand, you can ask me, and I'll just give you more information about this. Yeah, please.
Maybe you could have said some few words, more words about Boltzmann
Okay. Yeah, so about Boltzmann machine. So here, what to do? So Boltzmann machine is a type of graphical model in which we suggest that we have variables and we have hidden variables or explanatory variables which has certain dependencies among them. And we can see only some of the variables. Hidden variables are not available in data. We simply don't see them. So if someone knows what is hidden Markov model, I believe it's much more popular, then you can just recall what is hidden states and what is visual states. So in deep Boltzmann machine, we just suggest that there is joint distribution, joint probabilistic distribution on all these variables, and it's Gibbs distribution. So we want to find, we see all the variables available in our data, and we want to find values for hidden variables which fits the data mostly. So in fact, we want to find the parameters of Gibbs distribution which fits the data mostly, the data we see, and after that we just evaluate values for hidden variables.
Am I understanding correctly that you are saying that we have somewhere in weights we have distribution parameters?
Yep, exactly.
Okay, I see.
So that we simply, it's not really simply, but we just finding the values for hidden variables, and those we just learn restricted Boltzmann machine. After that, we use this to learn new layers of our neural network. We do not use labels. Instead of, we simply use data to build new representations for our data. In fact, we do the same thing as autoencoders, but in a more different way. We use suggestions about Gibbs sampling, and we, in fact, use some suggestions about the number of hidden variables. So that we build, after that we can say that we build representation of observed variables with hidden variables. After that we use hidden variables as new observed variables and use them to build a new layer of deep neural networks, doing the same thing, and so on. So why do we do this? In fact, as I already said, in the vanishing gradient problem, we have a problem that first layers will not receive much errors. So the weights in the beginning will not change. We must say that we will not learn them. Because they will, sometimes they will change, but really very small, with very small values. In order to avoid this, we just strictly learn first layers to have our data representation, which is not built on how good we are in predicting, but it's much more unsupervised way to do so. We're just building it in order to have a good data representation. So, was it clear?
Maybe one more question.
Yeah, please.
Am I understanding correctly that you're saying that we are just growing our network in the process of learning?
No, in fact, yeah. We not growing the network, we just sequentially build new weights. We have fixed the structure of network, so we know the number of layers, but we don't know the weights of these layers within which connects them. So we just first learn first number of weights, then the second, and so on. Doing so, we just learn the network, which had the fixed structure. We did not change the structure, but we simply learn the weights. yeah, in fact, we can also, there are works about this, how we can also learn the structure, so how we can adjust the number of hidden layers on each layer. But unfortunately, it works extremely long, and it do not really improve the performance. Yep, please.
May we use here some other graph module, for example, not fully connected or something?
Yep, yeah, there are no restrictions, of course, about using some other graphical models, but why? What for? In fact, they also will not improve, so they may improve performance, or we just can try to build something more complicated in terms of representation. Build not only the one layer, but build more complicatedly connected layers. But I also don't see if anyone uses these techniques. Okay, any more questions? Yeah, please.
I have a question, like general question. What do you recommend to start learning neural networks and to start using them? Which package? What to do?
Yep, okay.
How to start?
There are in fact lots of resources devoted to deep neural network. I believe that it's the most discussed topic in machine learning. It's obvious. So there are lots of libraries. Python is the most used for deep learning networks, and there are, I believe, more than 10 libraries to do so. The most used are Theano, Caffe, and TensorFlow. However, in most of other languages, there are lots of libraries to implement deep neural networks. So they also have they have structures, which I was talking about. So you don't have to build all these layers by yourself and implement backpropagation and so on. Okay, if you want to get deeper into models, okay, there are lots of materials. I just tell you, there is YouTube course by Nando de Freitas, yeah, thank you. So he's a good practitioner in deep learning. There is a course in Coursera by Geoffrey Hinton, father of deep networks. There are materials in Russian language about deep networks in wiki groups like Deep Learning. It's really cool group. So I believe, yeah, the key problem is that there is no kind of book about it because it's very fast growing topic.
What about the deep learning book?
Okay, yeah, there is one, but it's really outdated. So you can start with that, but yeah, I don't really see why people trying to write books about deep learning since they get outdated when it's just published. It's not really so interesting. So yeah, in fact, it's not kind of hidden knowledge, and what I said, Google and so on, you just can find lots of good materials about it.
Which package you use in your work?
So okay, now we use Theano. So in fact, yeah, I cannot say that it's just one package because in our lab we have lots of students who work and they use, in fact, what they want to use. There is no restrictions if they solve a separate problem. Yeah, but people who work in our lab and who do deep networks mostly use Theano. Yeah, sometimes it was Torch once, but now. Okay, so yeah, if you have no more questions, I'll just continue because I really didn't expect that I will go so quickly to the point. So what I was talking about was networks which we used to find certain dependencies, just like to predict something or to guess something and so on. But these days there is one very popular thing which is not only about discriminative models, but about generative models. And in fact, people who do not really relate it to machine learning may not know what is deep network, but they must hear about applications of generative network. So, first of all, we can learn representation with a deep network. And after we learn a representation with a deep network, we can use this representation to generate something new. And this is really what we expect from artificial intelligence. We really, of course, we want artificial intelligence to understand if he sees a girl or a boy. But we also want some creativity from artificial intelligence. And that is really what neural networks can do. So, the key idea is quite simple. We have a network which receives images and has an output, just imagine a class. So, for instance, in this paper, people focus mainly on chairs, also on cars, and but mostly on chairs. Why chairs? Because chairs are really complicated. There are lots of forms of chairs, many different, you can imagine. Just like this one, or something more ancient and more cute, or maybe a very simple wooden chair. And the problem of classifying these chairs to categories was really not so complicated, but really complicated. More complicated than some other problems. So first they learn the network which can predict what is the type of chair. After that, they just flip the network. So now they receive not an image of chair, but a label of chair. And the network should predict the image of a chair. So now you see there are convolutional layers, max pooling layers, but it goes not like here, but here. In fact, they use two networks, one for shape and one for coloring. And they predicted two images. So one image was just black-white shape, and second had to paint the shape, which was predicted by the first one, with colors. How did they do so? We just have an input. We can measure the difference between what we see and what we have. So we can learn a network which that has labels and images as an output, and then we just do the same thing as we did before. We just predicting, but not one, not a small number of labels, but predicting an image which is maybe similar to what we have already seen. Since we used lots of convolutional layers and we represented data well, we will not return only chairs we have seen. We'll generate something new, in fact. But most importantly, that we can say that we want to have our chair be something between one model and second model. And if we say so, the network should predict a picture which it had never seen, which has the chair inheriting properties of the first model and second model of chairs. So, okay, another thing is also quite similar, but is a bit more complicated and has a long history. It's a texture synthesis. So we have just like something like this, and we want to synthesize a new texture, which is very similar to this one. So the key idea is quite similar. We build so-called inner representation, which is represented with gram matrix. So we learn the network with images, and for each image we fix its representation. Representation is, in short terms, just what we have on convolutional layers before max pooling. So for each image we have its representation. After that, we have representation of the texture. So we can just sum them. So what we want to do, we want to build something new. We want to generate a texture which is very similar to one we had, but not just this image, something new. What we do, we just build a new network and put weights randomly. But after that, we want to learn weights so that the inner representation of our network will be similar to the one we had already learned. So that we'll be synthesizing a network that represents the same patterns. And then we use this network. It returns us a new image. It will be really similar to the one we had, but still it will be a new image. And this is how the problem of texture synthesis is solved these days. This was used to more artistic purposes. Okay, we want to translate styles. Style is the texture itself, in fact. So style is how our image is designed. And what we see on the image is just its image. So what we want to do, we want to mix. We have an image, we have a texture or style, and we want to apply this style for the image we have. In order to do so, we just need to do what we already learned. We need to build a network that has inner representation or gram matrix the same or mostly similar to the one we learned about this style. And we want to have the last max pooling layer for a new network as much close as possible to the image we had. So, in these terms, we just trying to build a network with two constraints that will be representing both style and image itself. So that is the network which was used for deep art. You may hear about this. You just load a picture and another picture, and it's just mixed the pictures. And Prisma, which then was found in 2016, used this algorithm to build a mobile application. It was really optimized, so it can do all these translations online in your mobile phone. And it used filters instead of new images. And it generates, so just apply. So you just load a picture, you just select a filter, and it's build a image. A neural network which generates this image is the more similar in terms of inner representation to this filter and in max pooling layer to this image. So this is how it works. Neural networks are not only to generate images, they are also used to generate lots of other things. So for instance, text, I believe Sergey will also talk about this, but this June in 2016, two Yandex researchers suggested, so they tried to learn songs, to learn a network which will generate songs like Igor Letov. So Igor Letov is a quite famous Russian poet and singer, and they created such a network. They just do kind of the same thing, but with recurrential neural networks, which should generate new texts. And these texts were really, some say that they are really similar to what Igor Letov could write. Also, nowadays, these networks are used to generate music. So we just want to have a new music piece, similar to the one we already had heard from Beethoven or Sex Pistols right now. However, it's not so successful as image generation. There are some inner problems with the architectures for that. Okay, any questions? So then I think that my talk is finished. Thank you very much.